So, welcome everyone. Third lecture of the course Software Maintenance, and today we are basically continuing directly from the last week's lecture. But before we get started, there's a small brief announcement I just said to the audience, but because most of the course participants are on the recorded lectures, I need to say it again so that it's also on the recording. So if you intend to join us next week on the lectures, don't, because I will not be here. I'm a work-related business trip, and unfortunately I will not be able to reliably be here on a Monday morning, so the lecture is replaced by last year's video. All the deadlines for exercises, events and stuff are in Moodle. They will open as if the lecture would have been given normally, and the only difference is that you will be using the last year's lecture with basically the same content. Small minor changes might have on the lecture sets, but still next week's lecture is from a recording. If you need a consultation hour for the course-related things or for the exercises or whatever you consider you need help with, please send email beforehand and schedule an appointment for the afternoon because the consultation hour, which is from 1 to 2, is also a bit problematic, but still I will be here later on the afternoon if some of you require help, or we can schedule something for the Tuesday. So please send email if you need a consultation hour help. So, as is usual on this course, we usually follow the course topics with new things so that they more or less are somehow related to each other. That's why we also start almost every one of these lectures with a quick recap from last week so that you get an idea on what was talked about and what topics were covered. Last week we were talking about the definitions of quality. So what is software quality? What is acceptable quality or useful or competitive or excessive quality? Meaning that what type of objectives you could have, or what type of quality objective you should have when you are developing software. Of course, the quality definition by itself is a bit annoying because it changes between the different types of apps, projects, customers, and so on and so on. So the most important part to take home from the last week's lecture was that you need to define what the quality is that you are aiming for. Basically, there are several different measurements, for example, the ISO IEC quality standardization, but that only gives us different characteristics, definitions, or for parts of the quality. Even though there are some characteristics which might seem immediately for more important than others, it's still somewhat vague on what's actually important where. And annoyingly, in the organizations we have been studying their definitions of quality, even the people working on the same project, in the same product or same service, in the same team, don't necessarily agree on what's the quality they need. So overall, they acknowledged, commonly accepted, good quality is a myth. So you need to define and you need to make a decision on what types of quality you want to have. Also, we covered some best practices or basic practices, more or less, with the intention that these are the things that are known to enable organizations or developers to do good quality. There were a list of things for agile developer, also a list of things for version control. But the important part was that these lists only more or less define what things seem to be working. Of course, if you have a group which doesn't have the necessary skills or capabilities or experience to do the work, you will have bad quality or poor quality, regardless of how you try to do things. But in general, following these sort of practices that seem to be functioning on most of the organizations, you enable at least the potential or the possibility that you might have something that comes out very good, or at least as good as it can be. But nevertheless, quality definition is something. Of course, if we put the objective somewhere, like we focus on security aspects and usability aspects or performance aspects or whatever, we only are so far in the process. We don't have the capability of yet measuring or understanding if we are at good enough level. I mean, for example, if we compare this idea to something like university courses, of course, we want to have this and that and those things, but still if we don't measure, collect feedback, or try to get the understanding of how the course works or functions, how well the passing rates are, how difficult technical the different things are, we can't actually do anything with the information, or at least we cannot steer the content towards certain direction. That's why we need to measure. We need to measure the software in a software project, or we need to measure the things we consider important for our quality objectives, so that we can understand that if our customers complain about something, that is there any truth in it? Is it just someone complaining because that's a funny thing to do, or trolling on the internet, or is it just something that annoys huge amount of users? For example, if we want to measure usability, we want to consider things like the amount of actions needed to achieve something, or the length of average session per customer. For example, in a web shop, something like Amazon or whatever it is, it would be probably worthwhile to measure how long it takes the customer to find the product, compare it against something else, put the product in their shopping basket and buy it. If this time prolongs much or becomes longer and longer and longer every time we make some adjustments, it means that probably the usability worsens. If we add too many activities required to buy things, the customers might change their mind before they actually push the put the order or pay via credit card or PayPal button. And that's of course a bad thing for our business, but it's also a bad thing design-wise, because we are actually actively hindering ourselves. So whatever we need to do with the quality, we need to measure that we are doing something right. And this is why we are talking about measurements in software on this lecture. So what is measurement? Basically, measurements are simply a process in which we try to define or collect information, relevant information over something that exists. We have several uses for the measurement. For example, there's a saying that we can't manage something that we don't measure, because using measurements gives us understanding on how things happen. There's no inherent things or visible clues that something might be wrong. If we are building a house and we are using bad concrete, we might have some visible clues that something's wrong here. Or if we are doing something stupid with the plumbing or air conditioning or something like that, it becomes obvious when we try to look, or well, when we try to set things to function correctly, or if we hire someone who is a professional to oversee or see our plans. But because in software we necessarily don't have this luxury of having a gift of sight or obvious problems in the design, we need to measure things so that we can understand what needs to be done, how probably even assess how difficult it will be, and also how good our software is or how functional our software process is. And that's the use of measurement. Also, when we understand how good we are or how bad we are, it allows us to control what we are doing. So we can predict outcomes, we can do changes, we can see that this is going to fail if we continue as is, so we need to do something. We can see, for example, on the example of the amount of input needed for a user to achieve something, or how much time the customer has to use on the web service to actually do something they are interested in. We can see well before the last customer leaves us that we are having a design problem, we are having an optimization problem, we are having a usability problem, simply because we have measurements which tells us that this is problematic, we need to do changes, we need to add more usability testing, or we need to do an additional cycle of algorithm optimization because this simply isn't working. Also considering, for example, where the errors are or how the errors are found. If most problems are found internally during the development, it probably means that most of our software process approaches or activities or tools and the infrastructure, development engine and such are good. But for example, if most of our problems are found by customers, simply because the system doesn't work, it might mean that we have to do some changes to the tools, the way we do testing, the way we do quality assurance work, and all these small things. But if we don't have measurements or understanding, we don't have control and we don't have the capability of influencing the decisions. And finally, of course, we do measurements to encourage improvement. So, okay, we might have good product, or we might have an acceptable service, or we might have acceptable process, meaning that we haven't failed yet. But still, if we want to improve or want to find things that we could improve, we need to measure stuff. So, there's a couple of ideas. So, developers who drink coffee in the morning produce better code than those who drink orange juice. True, false, who knows? The more you test the system, the more reliable it will be in the field. This is also something that's usually stuff that people think that this is obviously true. But unfortunately, it might not be that. For example, how do we know that our testing practices, how do we know that our test cases or the entire system actually corresponds to what we find in the field? We might have a perfect engine, for example, if we are running it in a simulation lab in an industrial building indoors, but when we put it in a real Formula 1 car, it fails miserably. This isn't actually something that just happens in small-scale stuff. For example, the Honda Formula 1 engine, when it was reintroduced a couple of years ago, was a huge disaster because it was tested, it was developed, it was based on existing technology that was known to be very good. But unfortunately, it wasn't reliable in the field because it had auxiliary problems. It had problems caused by actually being out in a car which runs 300 kilometers per hour on the track, causing it to have G-forces and having friction against different other parts or components, or having a pull which tried to unplug all the cabling or all the gas manifold and stuff like that. So it failed several ways after it left the testing work. So definitely not a simple or universal truth here. Also, if you add more people to a project, it will be completed faster. Of course, this barring the obvious situation when we have too few people to begin with. Obviously, if we add more people to a project, there will be some improvements, at least to a certain degree. However, most industry agree that you can only cut something like 40 to 50% of the completion time by adding more resources, whether it's money, people, or anything to a project, simply because after a certain point, the different teams start to hinder each other. Not necessarily because they hate each other, that's also a possibility, of course, but because they are doing the same work, or the possibility to coordinate the different teams is difficult, or the amount of independent work or the modules that teams are working in are simply too few, so that there's really not that much to do per team, and it starts to hinder the overall work because the teams have to coordinate with several different stakeholders on minute matters that don't necessarily require a full team or project group to handle. So, in all these situations, how do we prove or disprove these things? We more or less can give an opinion on all of these things. On the last two parts, there's examples which definitely tell us that they are not necessarily true. On several occasions they might be, but not necessarily always. And the first one, the developers who drink coffee in the morning produce better code than those who drink orange juice in the morning, might actually be very difficult to prove or disprove because the people are not the same. Some people are athletic, some people are couch potatoes. It might not be necessarily obvious, but I'm not known for running a marathon in my life. But anyway, drinking coffee helps someone, but on some other people it just causes them to have digestive problems. So is that helpful if they are running to the toilet for the entire morning? On the other hand, the orange juice doesn't necessarily do anything. It might as well be water. And overall, it also needs to take into account the people who don't like coffee or who drink tea. It has some caffeine in it. Does it have some effect on people? So obviously, it's really difficult to prove or disprove the first one because there's huge amount of variance in the environment. So, nevertheless, the difficulty is not a concern in a sense that all these things can be proved or disproved by doing measurements. So, there is no way around it. If we need to interview people, that's also a measurement, because the measurement is not necessarily just something on the dashboard of your car or the health report or something on your version control system. It might be just being interviews. If you need to know what the people are thinking about or how healthy your process is, you should start by asking people involved in the process. There's another saying that how do you measure or know which types of elevators are really popular in Saudi Arabia? It's a simple trick really. You take a flight to Saudi Arabia and go there and ask people and companies what sort of elevators are something that they are interested in. Do they need person elevators or freight elevators or what? Of course, there's several things you can measure. This is from the quality standardization from the last week's lecture. This same picture was shown then. And it's no surprise that it's actually, especially in software project, there's a huge amount of different sources of information. There's also a huge amount of different things you could observe, huge amount of different things that you could be aware of. So of course it's going to be completely impossible to measure everything and collect all the possible information, because of course you could do that, but it would also probably mean that you have a huge overhead, because you are basically just doing some sort of detective or police work on overseeing what other people are doing. Is that even useful? Now, well, in most cases, the most information isn't even useful for you. For example, what possible need would you have on knowing what's the typing speed average of certain developer, or how many test cases certain person writes on 1 hour, when the important part is to see how many tickets close, for example, during the cycle, how many serious bugs have been found and fixed on the system before it goes to limited release on next Friday. So basically, there's some basics on it. So if we are working with software and software process, we more or less can measure these 3 things: product, process, or people. The thing which we are working on. The product here is obviously because it needs to have a P starting word in it, but the product or service or whatever the thing is we are working with, the object in development. The process, of course, on this case means the way we are doing things, and not only on that project, but on the entire organization. How are we running things in general? Is the organization or company running the project imposing some problems or restrictions or hindrances to our work? We might have the best possible leadership, but for example, if we don't have enough tools, something like testware emulation system licenses, meaning that most of our people just sit on their desk waiting for their tools to free up so that they can run their own set. It means that the process is problematic. And actually this example isn't really far-fetched. There was a huge, well, still is, it hasn't gone the way of the dodo yet, but still there was a huge company making mobile applications on the time when the mobile phones were still sort of closed systems. You bought it with some applications in it, and you might buy 1 app per year if you happen to have the suitable Nokia set which supported that particular software upgrade. But still, the company made applications for the Nokia phones. Was really known for it, and actually had a large office here also in Lappeenranta. They had a problem in their main office in Vantaa, or one of their main offices in Vantaa. They didn't have enough allocated licenses for people to work with. They had 10 developers, but they had only 8 licenses per team, at least at that time. So basically, their reasoning for that was that there's always 2 people from a team of 10 who are away, or who are not doing that particular work, or who are sick, or who are in training, or whatever. But in reality, it also meant that on the days and sometimes weeks when the entire team was present, or if the team brought in more people from other teams, they still had the same restrictions. So sometimes people spent the entire day just waiting for 1 license to free up so that they could run the testware, run the emulated hardware, and see if the new changes or fixes actually function. And this was just throwing money away, but that's nevertheless the process problem. Not the product problem or the people problem. The people problems are cases where we have incompetent or hostile people, or lazy people, or somehow people who are not really interested in teamwork or cooperation, or even trying to achieve an end result. Of course, it's very controversial to measure people, at least here in Northern Europe, but still we can't say that the people aren't the problem. Of course they are. People have experience, people have knowledge, they have certain background, they might have their personal preferences, or they have varying opinion on how interesting or important this work is. And that also, of course, affects their output on the product. So, the product, but considering these things individually, if we measure the product, we of course measure the software system, the documentation, and all the other deliverables. Keep in mind that if the product isn't only the source code, it's not only the repository, it's not only the usability aspects of the front end or the technical aspects of the back end. It's also the documentation, all the deliverables, how the users or people who pay for the product see it. It also might be something that, like the size or functionalities offered, the costs, and other quality attributes which we have covered earlier. Even if our product is very good on functionality offered and cost area and size area, basically being something that's very well done, it might not be a good product or something that needs to be changed because, for example, it's still too expensive for our users, or it doesn't have the necessary things that the competition has, even though it completely fills out the specs we have for the product. So of course, the product, if we are measuring these things, we also need to measure it as a competitive thing, not only within our laboratory, but also in the entire ecosystem where it's used. This is also why, for example, the Honda Formula One engine was a spectacular failure, because although it offered huge amount of power for its size, and I think it was very cheap for the Formula One team to run, and it had quality attributes in its own testing environment, it still had several problems because, for example, it simply wasn't as good as its competition. And that's the product reason, not the process reason or the people reason, because it's about the product and its ability to, for example, withstand the external forces it encounters when it's in use. So if we measure process, of course, the way the product is developed, what life cycle do we use, what deliverables are produced, how do we analyze the deliverables, how do we do quality assurance, how do we do quality control work, how do we do requirements gathering or requirements engineering work, how do we identify the important parts that needs focus, how do we manage complexity, how do we manage builds, how do we manage software product lines, meaning that do we design things with common core and try to make a product line out of the product, or how do we even have a process for managing that? And finally, how can we make the process faster if everything else functions, or how can we make the process better, or instead of faster, for example, cheaper? Can we skip something unnecessary? Also, finally, the measurement of people. So we can measure different things. How fast do they work? How much bugs do they produce? How much they take sick days? How well they carry their weight in a project? But this is, of course, very controversial. It's something that you could measure or can measure, but usually this is very a bad thing to do, at least publicly. Of course, I know that every organization does it at some point. I know, for example, that I am probably being analyzed by someone in the administration or the payroll simply by numbers I produce. But of course, they're not going to start treating me like a number generating thing, hopefully. Because people don't like being turned into just numbers. Of course, there's always variance, there's always reasons. There's some people who are better at the work than some other. For example, if you have a real life professional software developer, that one person can replace 7 to 10 people who are beginners or not very far into their career as software engineer. So one real professional can replace an entire development team because they are so good. On the other hand, one team of beginners or novices or trainees cannot replace one professional because they simply lack the capability of understanding how the system should work. So of course, there are variances with people, but the measuring of the people or controlling people just as numbers isn't really the thing you want to do if you are running a software project. So, we can measure product, or we can measure the process, or we can measure the people. So now the next challenge is to collect the information. We could do weekly interviews with people. We could make everyone fill out forms. We could do several things to collect information, but unfortunately, it's usually the problem that we need to have useful information that's collect in a way that isn't a burden to the organization. Of course, the measurements and the data which we can use to control or enhance our work can be lifesaver in a long haul, but still, if we are intervening the people who are working, or being a burden with that you have to fill out the timesheets with 5-minute accuracy, so that they can, the administration can manage what you are actually doing. It is really bad for the work. Of course, it costs money because people are filling out forms or making the measurements. It also means that people start automating or doing bad work with the data collection tools, and we don't actually get useful information if we know or if our participants need to fake the data or just fill it so that it isn't suspicious. If we want to be unintrusive, if we want to make the data collection automatic, those are very good things, but on the other hand, it can be expensive. And unfortunately, having been working with the empirical software engineering approach and working with tens of software developing teams and organizations in my history, I know that it's really difficult to convince the upper management to actually try out something that isn't immediately obvious. Because if we are collecting more information from team or more information from our product, which doesn't immediately add to the value, but might save us some time or problems in the future, it's really hard to tell the management that we need to, for example, spend 1 person month of time making these automated scripts to collect information about this and this and that, or do the analysis on the user feedback or the bug report database so that we can understand what is working and what is not. So even if you become a software lead developer or someone who is responsible for managing a team, it can be problematic to implement the data collection tools beyond what you have automatically with your development tools and the other software infrastructure. So basically, this is more or less what happens. This is basically taken directly from how the software standardization sees how world goes around. So, of course, we want to measure something. We want to understand the software quality or the product quality. We need to have a goal of what data do we need? What data is relevant? What is important? On what has been achieved when we are satisfied with our data collection approaches? So, what are the questions of interest? Do we have categories? How do we establish that we have data on all the necessary categories we need to measure? If we need to measure the security or usability or our extra image, how people see our product or services from outside world, then of course we probably need to have some way to collect data for all these categories. When we collect the data, we of course then need to have tools, whether it's automated or interviews or whatever, try to be unintrusive, try to do it cheap. Of course, usually you can't, but still. And then when you collect the data, you need to validate it. So is this something that's accurate? Is this something that's usable? Is this something that was collected with methods from organ peoples or participants who were willing to give me the information and are most likely not to lead me to some direction? Or, for example, in many questionnaires, the problem is that you define a set of questions where you just want to confirm your suspicion. You don't even, not necessarily even meant to do that, but sometimes the data collection instruments can be really tricky to define because it might mean that you are unconsciously just confirming your suspicion. The questions are asked in a way that it doesn't allow anything radically different to appear. Very common approach or problem in this area is, for example, if we ask about the open source and the third-party tools. The questions might be something like, I think open source tools are difficult to install, or open source tools are difficult to use, and then the third-party or bought to commercial tools are too expensive. Of course, these are all things that you should care for. But for example, this leaves out the possibility that the commercial tools are difficult to install or difficult to use, or they don't have the usability aspect in their mind, or that open source tools actually cause additional costs with the support and maintenance work and stuff like that, which has to be done in-house, because for not all open source tools there are ways to buy support, or you need to buy some really expensive expert services. So of course you get completely correct information, but you might not actually get anything useful out of it. The open source tools could be better because you buy it with exactly €0, but on the other hand, you need to do something as a company which is much more costly than commercial tools. Or that the commercial tools are always designed in a way that they are easy and intuitive to use. Of course, who has ever used any tool in existence knows that this is not true. There's even in something simple like Excel or Word, a huge amount of settings and things which are really hard to understand or really hard to use, or if you need to do one specific thing in something like 3D modeling tool, it can be really painful to get it right because the system somehow constantly keeps fighting you against doing the things you intend to do. And finally, of course, when you have the validated data or know that you have something useful, then you need to get the ideas out of it. So analyze it. How do we do that? How do we do analysis of interview data? How do we do analysis of survey data? How do we do analysis of PAC database? And so on and so on. And what is the appropriate level of alarm. So if you have 1,000 survey data sets and 50 of the participants complain that the tool is too difficult to use, is it worthwhile? 5% of people complaining that it's too difficult to use. Some would say that it isn't. 10% would be something, but 5% of the users isn't yet important. But on the other hand, if it's the only thing that's really bothering some group of people, there's too many button clicks before I get anything done, it still might be worthwhile to investigate, even though it's a minority problem. But if it's the most important or glaring problem, it still might be a minority problem, but it's still the most important problem you encounter. So, there's, for example, a couple of companies, what they try to do. These are all huge, large companies, Motorola, Hewlett-Packard, these, some would say dinosaurs of software engineering and ICT industry. So, for example, Motorola has the 7 goals. So, whatever we are doing with our metrics programs, we improve project planning, increase defect containment, increase software reliability, decrease defect density, improve customer service, reduce the cost of non-conformance, and increase software productivity. So whatever we are measuring, whatever we are doing, we try to improve these things. These are the important things for us. These are the things we try to thrive on. It's a fairly simple approach. These are the things we try to do. Whatever we do, we try to get all of them, most of them, some of them, or at least one of them. So if we put money on it. IBM, similar, Software Measurement Council. Set of metrics, call it 5UP, which define customer satisfaction, post-release defect rates, customer problem calls, fixed response time, number of defective files. Of course, IBMs are now a data center organization, so I'd say that number of defective fixes or fixed responsive time or customer problem calls are probably quite important because they are doing something that's very costly for the customer if their system fails. Of course, because they are on this area, the customer satisfaction and fixed response times are very important, because if they are not very good at that, then the organization which uses IBM software or IBM management system or IBM infrastructure or ecosystem to run their data systems, they are going to switch to somewhere else if the customer service isn't working or if something stupid happens. And of course, this also shows that they really are not very interested in things not related to customers. So customers mean everything. If they measure things that more or less are only stuff that affects the customer image or customer view of their service, because that's where their business lies. Similarly, as for example, with some other company like Toyota, one of the things they measure is the just-in-time completion percentage. So how much overhead do we need to have on car manufacturing, or how much extra parts we need to run a full capacity production line? Of course, those are important to Toyota because they want to make cars with minimal overhead as possible, but IBM is about customers. So if IBM were to make cars, it would be about the customer satisfaction, how many recalls do they need to have, how fast their service centers are, how many problems the customers encounter, and how many faulty parts there are in their cars, and nothing else. But IBM isn't in the car business, so they are focusing on the customer service. Finally, the Hewlett-Packard is a process company. So average fixes per day, average engineering hours per fix, average reported defects per working day, and defects over testing time. So unlike the other companies mentioned here, Hewlett-Packard is actually interested in how well their projects or processes work. They don't necessarily, of course it would be wrong to say that they don't care about their product. Of course they do, because that's how they make money, but the thing that really interests them is that how many fixes did we get. It also implies that they are interested in how well we are able to get rid of the problems, how the defects accumulate over time. Are the defects found on the early parts of the project, which would mean that they are something that's easily squished, or that our product, when it's launched, most of the problems are found immediately and then it's just smooth sailing to the end of the life cycle? Or are we always hitting spike or major release or major revision, meaning that there's something problematic in our defection detection or quality assurance practices? So you can measure different things, and of course for these things you need different types of measurements. So there's a couple of words here. This is just something that's fairly simple stuff. So measurement or measure, it's something like comparing to a standard approach. Metric is a definition of what element we are working with, and the indicator is a thing we can use to show what has been achieved. And basically things that you probably already know. On the other hand, it doesn't matter what we are trying to measure. I mentioned already that there's the validity problem of the measurements. So we might have a situation where the system lies or gives us false sense of security because we are measuring wrong things, or we just get unreliable measurements. And these are actually important parts, because reliability and validity are the only two things that actually matter when we are doing measurements. We need to have product measurements which are reliable, so we can work based on them, and valid means that it actually measures the right things. So basically, these targets here represent all the different things that might happen. The first one is reliable but not valid. We see that the measurements are in the same area, meaning that whatever it measures very well that area. Unfortunately, that's not something that we need. The other measurement is valid but not reliable, meaning that it's all over the place, but the midpoint seems to be where we want it to be. So of course it gives us some indicator, but it's not really usable, because the result might actually be anything. And finally, the last one is reliable and valid. It measures the things that we need to know, things that are useful for us, and it measures it in a way that we get useful information out of it. So we always try to achieve the last one when we are measuring things. And in large organization, the measurement or how we decide what to measure, we usually do a measurement plan. Like I mentioned earlier, we need to have quality characteristics or aspects we want to measure. Then we need to have the categories and the definition that we will have the information or something that we can use on all the areas which are important to us. And of course, if we are doing work in a large organization, it's easy to just say that, oh, this is someone else's problem, I don't care, meaning that no one does it. So basically, the software process standardization, test process standardization, says that if we want to actually have a measurement, we need to have a measurement plan which indicates things like why we do this, what we measure, who will measure, from what parts of the system, when it's done, and how it will be collected and analyzed. This isn't something that's a Bible, but more important. It's something that's part of the testing plan. So when we measure things, what we measure, who will do it, where it will be reported, what things are exempt from the measurements. For example, if we are running several parallel branches of the product, do we provide measurements from the experimental parts? Well, probably not, because it's experimental for a reason, but still, it needs to be said somewhere. Also, how we will use the data. How will it provide us useful information? Because then we know by the end of the project, if it did work, then we keep using that. If it didn't work, or if we had to abandon the approach because it was too laborious, or too expensive to use, or too time-consuming approach, then we need to tone it down. And that's, of course, something that's also part of the process improvement. So, of course, we need to think about money, or what is reasonable thing to do. So how do we define the measurements so that it actually affects the business? So we can't just add extra work to organization. No one is going to pay for just adding unnecessary extra work. So how do we ensure that this is actually something that's useful to us? How do we ensure that the results are reliable? And how do we ensure that the results are understandable? If it's a number between 0 and 100, and there's no explanation what it means, then of course it's not useful information. And also it should be something that explains us what do we need to focus on. On the best scenario, the results can even indicate what component or event caused this result. If we have problems with system performance, then we might have something else going on, like were we under a security attack? Were this the time of the year when we have traditionally many customers? How can we actually even know when we have customers and such and such and such? And this is about the selectivity and the measurements which affect the business. Even though we might be only interested in those customers who use their credit card to buy stuff from us, we might still be interested in people visiting our website or using our service, because this gives us an idea on when people are interested in our products. And it also can give us the opportunity or ability to predict that if our user rates or amount of users go up, then the spikes get larger, and then we need to consider if our hardware can even handle all these things. This sounds something that's very simplistic and very simple, but keep in mind that this Christmas sales season, both Gigantti and Verkkokauppa.com online stores failed to work when people went in to look for the Black Friday sales. And this is something that's, irresponsibly stupid, if you ask from me. If you are a web sales company and you try to sell stuff to people and your system completely fails on Black Friday, you just messed up your best sales day of the year simply by being ignorant on measuring or trying to understand if your system can even handle that much that much traffic. Anyway, if we try to summarize up a bit on all the different measurements which are defined by different documentations, whether it's standardization or industry practices or whatever, which you can find from the course website at Moodle, there's 4 things that you need to have on your measurement or metric. It needs to be objective, so that it's not dependent on the people or environment where the measurement is made. It needs to be reliable, so the accuracy, repeatability, and usability is able to produce precise and readable results. It has to be economical so that it's usable in a sense that it saves more money than the measurement costs, and it needs to be reusable, meaning that the things you measure are repeatable so that you can compare the old results and new results against each other and understand perhaps why these things keep happening. This is all that is to measurements. Whatever metric, whatever measurement you use, it has to fulfill these four objectives. So, the ISO IEC 29119 testing process standard is actually full of different ways of measuring things. I'm not going to go through these things here because there's literally hundreds of different ways to assess usability or security or all the different things that you could actually want to assess. So there's raw and general data-based measurements, work plans, project status, system completeness, test result-based, reliably based, and quality assurance efficiency-based indicators. These are the main categories. On each of them there's several tens of different measurements or things that you should probably include. Of course, it's not meant that you use all of them all the time, but you pick some of them so that you can use them as your basis. Of course, combine this with the ISO IEC 25010, the software quality standard, you get more measurements for directly the different attributes, whether it's in quality, general quality or quality in use attributes. You have wealth of things you could do or things that you could use to assess your product, your process, or your people. For an example, the basic measurements on the standardization mean basically these sort of things. So remaining budget versus remaining time, the amount of features versus remaining time, the amount of features, lines of code, amounts of bugs, so on and so on. So basically really simple things, and probably something that every worthwhile software product or service launch or management tool or environment can handle. So you get this information out, you get some idea on how far your project is or if you have any possibility to ever complete your work. Of course, they are easy to use, but they yield relatively low amount of actually useful information. For example, on the last lecture it was mentioned that the complexity of the different components, of course, varies to a certain degree. So some parts are really straightforward. They are just there to provide some functionality, like listen to the network, send packages forward and backwards, do some simple stuff, draw the user interface, simple things. But then there's also some other parts like the artificial intelligence or the automation tools or whatever, which might be hugely more complex and difficult to create. So of course you need to identify these things because it's usually a fairly good idea to focus or spend resources on getting these components functioning before everything else, because if you know that you made the most complex or difficult part of your system and it works, then the rest is just coloring between the lines and making the system work. So, of course, the basic measurements like the amount of money left or amount of work left or amount of features left doesn't really yield useful information on this area. So that's why these next few things are actually something that's useful to assess these sort of things. The first one is functioning points, or function points. In this approach, we don't actually measure the size, but we measure the functionality offered by the system. This is something that was originally developed by IBM to assess especially the problematic areas or the possibly problematic areas of the different modules, so that you could have a sort of idea how complex or difficult things will be. So basically, we offer the functionality offered by one subsystem or component or module. So this definition or the calculation can be done when we have the definition of the module. So what it needs to do, how it needs to work, what it needs to use, and so on and so on. And these don't even care about the programming language or anything, because it basically takes into account the external inputs, the external outputs, internal files, external interfaces, and external inquiries. These things, how many of these things the module has. So basically, you count the amount of them, and following this formula, you get a number. The number doesn't have any relative importance. Only importance is that higher the number, the more relatively complex the component is, and of course the component with the highest number is the most complex part. So basically a description like this, if we color out the parts which indicate that this is a feature, this is a file, this is an interface, and so on, we come up with numbers. So 2 external outputs, 1 external input, 1 logical internal file, and 1 external inquiry. Combining these, that functionality would have function point score of 28. It doesn't mean anything in the universal scale, but if it's the largest number of your entire system or the modules you are developing, that would probably be the complex part. Of course, the original way of doing this calculation was defined in the 70s. So, of course, it's sufficient to a certain degree, but unfortunately, later research into the approach showed that it correlates quite closely to the lines of code estimates. Ways of understanding that, okay, if feature requires this much code, then this and this and this, so that's going to be a problem. But do not worry, it was extended later on with the general system characteristics, and it tries to get more definitions or more details out of the system. So basically it tries to give you an idea on what sort of things you should focus on. And there's actually 14 questions about the system, and it defines these sort of things. So data communications, distributed functions, performance, configurations, transaction rate, online data entries, end user efficiency, so on and so on and so on. So it takes into account several other things. Of course, important part here is that you can do this once with your first architecture design, and it would give you a sort of estimate on what are the important parts that you need to do. Not going into the details on how that's done, you can Google that after the lecture, because using that model would probably be an entire own course. We define different factors that how important this thing is for us, and then sum up the factors and the points given on that basis. So end score on these, based on the previous example, which I'm doing as a cooking show approach here, saying that we prepared this earlier, would be something like this. Okay, so with these factors from 0 to 5, and with the questions how important these things are, how many of these things there will be, means that we get internal score of 25. Okay? Not huge difference, from 28 to 25. But the point here is that the extension takes into account more factors. It doesn't correlate anymore only with the lines of code approach, but it still gives you relatively good estimate on how much work there will be on this module. So how difficult will it be to create, and how much focus or how much resources this will probably need. Of course, if it's something that you can take from your software product line core library and just tailor it to your new product, it means that the most of the part is already done. But if you are creating something from scratch, then following this complexity, function point calculation could yield you something to start working with. But of course, that isn't the only way of measuring things. If you are measuring function points, you are probably quite far already, but you can also measure something like cyclomatic complexity. So this again is a way of defining how complex this module will be. The unfortunate part with the cyclomatic complexity is that this more or less requires you to create a graph of how the system internally works, the activity diagram on what happens when the system works. So basically, we calculate the number of edges and nodes on the flow chart on how the module and system will work. And it will give us a cyclomatic complexity. So basically, on this type of function, so basically it gives you, that gets a random number, and you try to guess the number enough times so that you get the correct answer. This would have a cyclomatic complexity of 3 because it has 3 different paths it can take. So basically the cyclomatic complexity is equal to the number of different paths you can take on the program when you are using it on that module. Of course, it means that if you have a larger number of paths you can take in unique paths from start to finish, then more complex the module or the system will be. And in fact, this has been studied. And the value of 10 is the point of no return. If your modules or components all have cyclomatic complexity of less than 10, you probably don't have problems caused inherently by making it too overly complicated subsystems or components. But if it's more than 10, and if it's really much more than 10, then you probably need to do refactoring or re-engineering work, because you will have a huge supernova or superstar class or superstar module, which will ruin your day when you're trying to maintain or use that anywhere. So you need to split it up or do something to reduce its internal complexity. And this is actually something that's widely used and accepted in the industry. If your cyclomatic complexity of any module is more than 10, you probably need to do refactoring and re-engineering work. Based on these numbers, there's also the Halstead software mathematics and computations. Basically, the idea is that every program ever made will be a long list of actions and values. So we can more or less define what the things like complexity or difficulty or probability of problems or the amount of errors in the system by just making a calculation on how long the source code of this module is, or how much work has been done to develop this module, because over the large amount of data, the amount of errors per lines of code actually starts to follow a normal distribution. So we count how many distinct operators there are in a program. So how many variables, for example, how many distinct operands are in a program, how many different types of actions can be taken, how many times these operators are called, how many times these operands are called. And based on these primitive measurements, we can do assessment on the complexity and difficulty of the system. So, of course, the vocabulary is the different unique actions plus the different unique functions or names. The length, of course, is the amount of the actual length of or the amount of calls for both of them. Volume is basically how many bits it will require to represent this as a program. Level means complexity on this calculation. Difficulty means how difficult it will be to create, how much time will be used to create it, and how many faults it will have. And on this, following this calculation, for example, the S is the average number of decisions between errors. And actually, there's a, yet again, generally agreed thing by the industry that 3,000 average number of decisions are done before between the different errors. Meaning that if we have industrial or commercial grade product, it will have one error or one problem per 3,000 actions, whether it's calling or using a variable or using an operand or doing a function call or whatever. If you have 3,000 distinct activities, you are prone to have at least one error in the system. And this, of course, meaning that if we have a long-standing, well-maintained, otherwise sort of same product, so we can expect that we should have at least this amount of problems in it. And if we find that amount of problems, it of course doesn't mean that the software is done, it's bug-free. It just means that we have probably found all the most probable or usual problems in the software. And finally, following all these mathematics approaches, there's also the defect arrival pattern. So like I mentioned earlier in this lecture, it does have actually matter when we find the problems. If we find the problem when we are doing first development for the first launch, and then we don't find anything after we do the alpha, beta release, or put the product into the market, it means that probably our quality assurance work is done fairly well. But on the other hand, if we have a huge spike of problems for every time we launch or put some new patch up, it probably means that there are problems in the way we are doing testing work or on our test coverage or quality assurance or test automation. For example, these examples. We can expect that these have the same total amount of reported bugs. Of course, it might not be that, but still, let's say that these 2 weeks have the same amount of bugs. The one on the left side looks good. When we launch the product or put it up for system testing, we find huge number of stuff, and every time we launch a new feature or new patch or addition or daily or whatever, we have some new problems, but the overall amount is declining all the time. So probably the cumulative rate is flattening out, meaning that the product was developed with the software engineering or software quality assurance practices which are sane, and it's probable that unless we release a faulty patch, we will not encounter any huge problems. On the right side, the amount of the defect arrival rate or pattern is more or less random, and more worryingly, it's rising. So we have a problem that we are fixing bad fixes with worse fixes, even though we at one point were very close to not finding anything. But on the other hand, we do not know if the rise of the number here or increased numbers in the end of the line are caused by new problems or new patches being faulty, or that we didn't find them to begin with. But still, it definitely means that something's wrong here, and even if the relative amount of errors is, the absolute amount of errors is the same, I'd say that you have to be insane if you want to have the project on the right side instead of the project on the left side. So it means that also these sort of things actually do matter, and this is something that you can't see if you are just observing the absolute amount of different problems. How they are found and when they are found is also very important. So you should aim for an approach which stabilizes towards the end. That means that your practices are more or less well done and you probably are doing something right. Or if you have a rising number of problems throughout the patching work, then you probably need to find what's wrong with your practices of quality assurance. So anyway, there's a couple of ways to use the arrival pattern to your help. For example, of course, there's going to be spikes every time you release something. Every time you do a patching work or release something new feature or stuff like that, it will probably have some problems you might not have found earlier. But still, even though there's the same sort of old wives' tales or the same idioms we use also on the introduction to software engineering hold also here. So we need to detect the things early. We need to track defects throughout the life cycle. We want to know when it arrived or when it first appeared, instead of just is it in the system right now or not. And also we should try to work on our measurement process so that if we have a rising amount of problems or the defect arrival pattern is rising towards the end, we need to know why this is happening or what could be done to avoid the problem or what is causing our software to suffer increased amount of errors when it hits the maintenance phase. Of course, this being the software maintenance course, that's something fairly important. So probably in that case, you have a problem somewhere between the first development cycle and the maintenance or update cycle, because you are probably not doing good enough job on the quality assurance practices of the maintenance work. Anyway, if we do this sort of work, we probably will have something like we have these sort of profiles. Of course, these are quite self-explanatory. If we find most defects before testing work or before official acceptance testing work on the first launch or alpha, then we are golden. If we look like this, we need to revise our quality assurance work or quality assurance processes. And of course, if we want to find some things that are also useful in a sense but are not perhaps immediately obvious, these are things that are identified by the industry. So fixed response time, how much time it takes to fix a problem. This was something that IBM was very interested in. The fixed quality. So how large percentage of fixes have been defective? How many rollbacks have we done to fix our faulty patches? And how many problems are causing shutdowns or delays or things which are not very good if we are trying to run our software business or product in a way we intend to do it. Of course, if we use the function points as a basis, then how much it costs to create one function point? How much time does it require to develop a function point? How many defects were caused by that? And how many defects were produced by a function point if we are extending the original function point approach? But like I mentioned earlier, people do not like being measured or negatively competed against each other. If you want to find hilarious examples of how this backfires spectacularly, go read about gamification and about the Disney Holiday Resort, where there was actually a war of terror between the different maintenance crews when they were competing against each other, trying to get extra chocolate bars and something like $100 bonus for being the best performing maintenance team in the resort park during the holiday season. So they started to put cement into the washing machines and using quick glue to break locks inside the maintenance building so that the other teams would have to spend time fixing their infrastructure. So that was probably not what they wanted, but that was caused by Disney being an enlightened leader or dictator and deciding that they start to compete people against each other for chocolate bars and meaningless bonus. So don't do that. Okay, so let's wrap up things. So, okay, this might not be the most interesting thing in the world, but still, these are more or less the fundamental basis of how software maintenance and software development cycle is done once you have the product out and available for your customers. So if you need to remember something from this lecture, it probably should be the definition of software metrics and measurements. Why do we measure things, and what are we trying to achieve by measuring things? We can't manage something that we can't measure, and we can't know something that we don't observe. Also, what are the different types of measurements? What are common for software development? What are the ways of, for example, helping out the design work or focusing your work effort towards the components that need the effort or need special care so that they don't backfire spectacularly. And finally, select your project group, and please select your open source project and register it. There's like 2 or 3 groups at this point. There's more than 30 students on this course this spring, so there has to be more than 2 or 3 groups. So register your open source project, first come, first serve, and remember there will be no live lecture next week. But week after that, we will be continuing as normal. So, thank you, and have a nice rest of the day.